Hello everyone. In the previous lecture, we have studied about refraction, the cause for refraction, the laws of refraction, and also some examples based on refraction. In this lecture, we will continue forward with the study on ray optics. The first topic here is called as lateral shift or lateral displacement. To understand this, look at the example given here. There is a glass slab and light enters from a medium to another medium. If we imagine that this is a rarer medium and the glass slab is a denser medium, so there is also air below this glass slab. So basically this glass slab is placed in air. Then if you look at the light ray falling on the glass slab, if we draw a normal at this point, this light ray is moving from rarer to denser medium. The angle here is called as angle of incidence I. If suppose the glass slab was not there, light would have gone straight like this. Light wouldn't have been deviated, it would have gone straight like this. But because of presence of a glass slab, light is refracted. So in the first boundary, light would bend towards the normal. Let this angle be here called as angle of refraction R. Again here also, if we draw a boundary at this surface, the light is moving from rarer to denser medium. So light would emerge out like this. In this boundary, light is moving from denser to rarer medium. So light would go away from normal. Since the above medium and this medium is same, what is seen is that the light ray which finally comes out, this light ray is parallel to the original direction of incident light ray. So this light ray is shifted by an amount, and this shift is called as lateral shift or lateral displacement. It basically means it is the sideways shift. To define this, we can say it is the perpendicular distance between the incident ray and emergent ray. Now for the entire slab as given here, for the slab, if we look at the surface PQ, for surface PQ, PO is incident ray and then OR is the refracted ray. For surface DC, this O dash is the incident ray and then O dash Q is a refracted ray. But for the entire arrangement, the entire system, this PO is called as incident ray, O dash is called as refracted ray, and O dash Q is called as emergent ray. So emergent ray means the ray which finally comes out of the system. In this case, EQ is emergent ray. As seen here, EQ or O dash Q, this O dash Q, E is angle made here, O dash Q is parallel to PQ or PL, because the PL is the direction of incident ray. So this distance here is called as lateral shift. We'll try to find out what is lateral shift in terms of theta as well as other angles. As drawn here, as seen in the diagram here, for the first interface, PO is the incident ray. So the angle made here is angle of incidence I. Now in this case, what we'll do is, we need to find what is OL. We learnt in the previous lecture that if you have a light ray which falls on an interface, if we assume that the light ray moves from rarer to denser medium, then light would bend towards normal. So instead of going along this direction, instead of going like this, light would bend towards normal such that light would emerge out like this. If this angle is I and if this angle is R, then this would be delta, which is called as angle of deviation. This delta is equal to I minus R. This is what is delta. So with that in mind, we'll start the derivation. So here we need to find what is O dash L. Again, if you look at the slab here as given here, this is normal at this point and this is normal for this surface. This angle is R. If you observe carefully, these two are parallel lines and the light ray is a transversal. Therefore, even this also would be R by geometry. So from this triangle, we look at triangle O dash L. So from triangle O dash L, we'll find, you want to find what is O dash L. We'll find from here sine delta. So from this triangle, sine delta is equal to, it will be O dash L by the hypotenuse, which is O dash. Now do remember, we need to find what is O dash L only. So from here, O dash L would be sine delta into O dash. But we don't know what is O dash itself. To solve this, we'll take another triangle. So we'll take triangle O dash as given here. It's like this. This is N O dash. The angle here between O dash is R, and then if the thickness of the slab is T, for example, thickness of this is T, then this also would be T only. So this would be T. We need to find what is O dash and also in terms of T. So we need to connect some trigonometric function with ON. So we know what is T and the hypotenuse. So the simplest thing would be to use cosine. From here, cos R is equal to T by O dash. Now from this, we get O dash is equal to T by cos R. Putting it back here, O dash L is equal to sine delta, but delta is I minus R. So sine of I minus R into O dash, which is T into cos R. So this is expression for lateral shift, where T is the thickness of the slab, I is angle of incidence, and R is angle of refraction. The next topic here is called as normal shift. Normal here means perpendicular. That's the meaning of normal in mathematics. It is called as perpendicular. To understand this, let us recall experiment which most of us would have done in school days. That is, if we take a case where we place something, for example a coin, at the bottom of this glass, and if we see from top, you would see that the coin would be at its original position. Suppose if we start to fill water or some liquid, water is most transparent, so if we fill water in this liquid and observe carefully, we would find that this object would have been shifted. That is, we would find the image somewhere here called as I. In case if you pour more water, it will shift further. So this shift between the original position and the apparent position, this shift is called as normal shift. Again, this happens because of refraction. As seen here, if we draw light ray from this object like a coin, draw normal here, the light ray bends away from normal because light is traveling from denser to rarer medium. So if you draw this light ray backwards, it appears as if the light is coming from some point here, and that point here would be the image. So this is where the coin appears to be present. So it is the apparent shift in the position of the object along the normal. It's called as normal shift. So if you draw normal to the surface, this is what is normal. So the shift happening along the normal is called as normal shift. We can have two cases here. A case 1 where object is in denser medium and observer in rarer medium. For example, think of a coin placed in water, or think, for example, of a fish as seen by a bird. We'll generalize it here and let us assume that we have a boundary, an interface. Let the above medium be called as rarer medium. So this is the rarer medium and this would be the denser medium. Let their refractive indices be n suffix r and n suffix d. Now suppose imagine that at some point here an object is placed. Now as seen from an observer from the rarer medium, we will see as to where will the object appear, that is the image appear. Let the distance between the interface and the object be called as XR. XR stands for real depth, that is where it is present. But because of refraction, the object appears to be shifted along the normal. To understand this, let's draw few light rays from the object. Let's take one light ray which falls normally along the surface, and we saw in the previous class that this light ray would move undeviated, move as it is. Suppose if you take one more light ray at an angle to the normal, somewhere like this. So this light ray falls at an angle to the normal. So if you draw normal at this point, light ray is moving from denser to rarer medium, and this light ray would bend away from normal. It will bend and go out like this. If we draw this light ray backwards, it appears as though the light is coming from this point. So this point here is called as image point. So the distance between the surface to this is called as XA. XA stands for apparent depth. Now apparent means something which is not permanent, something which exists only for a given time. In this case, what it means is that suppose this medium, think of this as water. Suppose if the water is drained away, if it's removed, then this would change. So this apparent depth exists as long as there is change in the refractive index of the two mediums. Once the medium is removed or it's the same medium, you would find real depth only. Now here we need to find out how are they connected. Again, here use common sense. Now x real is more than x apparent because here the reference point is the topmost boundary which separates the two medium. So if you put it back here, then x real is equal to x apparent into ratio of the two refractive indices. That is because the left hand side contains dimension of distance, and even this also should be distance only. So it will be a ratio of the two refractive indices. Since xr is more than xa, what we get would be nd by nr. It's again based on common sense because xr is more than xa. Now if you want to find what is x apparent is equal to x real into nr by nd. So this is the required formula between the two depths. Now the object appears to be shifted by some distance. So this OI is called as normal shift. So normal shift, which I write as NS, that is equal to, it will be x real minus x apparent. Because it is OI, that is equal to x real is as it is, and x apparent from this equation would be x real into nr by nd. Now from here, if we pull out x real or x r as common, then what remains is it is 1 minus nr by nd. So this is the formula for normal shift. In many cases, what we find is, we find that the other medium would be generally air, and then this would be called as H thickness. To make sense out of it, think that we have a glass slab like this, and then an object is placed somewhere here. Think of object O, and somewhere here is the apparent image position. Suppose if the thickness of the glass slab is T, and this is air, and this is glass slab, so here we have only one medium. So let n be its refractive index. In this case, this formula would take the form normal shift is equal to, it will be T, because x real becomes the thickness of the material, T into 1 minus 1 by n. This is what you find in many books, but then always learn the general formula because you can always go from here to here. So suppose if there are two different mediums, it is difficult to go from here to here. So always learn the general formulas. Now suppose instead of one medium, we have more than one medium. For example, look at a medium like this. We have medium like this, one medium, and one more medium like this, and then one more medium here, different mediums. In this case, let its index be n1 and thickness of this be t1. Let this refractive index be n2, thickness be t2, and this n3, thickness is t3, and let this be air. Suppose imagine here an object is placed. So based on the height, based on thickness and refractive indexes, we may get image somewhere, could be anywhere here, we call it as I. So in this case, if you write it, then the apparent thickness as seen in the previous slide, if you add for all the things, it becomes T1 by N1 plus T2 by N2 plus T3 by N3. This is what we get, because previously we had x apparent was x real into nr by n dense. If this x real is the thickness of the material and N surrounding medium would be air. This is what we get. This is adding for the 3 mediums. If you have more mediums, just extend the same form. The normal shift will be equal to, it will be T1 into 1 minus 1 by N1 plus T2 into 1 minus 1 by N2 plus T3 into 1 minus 1 by N3. It goes like this. So this is the expression for normal shift when we have more than one material. I do remember in this case a very important point, that the normal shift doesn't matter as to where is the observer. It's very important. Whether the observer is somewhere here, or seeing from far away, or somewhere from here, it doesn't matter at all. Because what matters here from the expression is that it only matters on 2 parameters. It only matters on their relative refractive indices and also the height of this medium. But the effective distance between the object and the observer would change. The normal shift doesn't matter at all. Whether the observer is somewhere here or somewhere here, the normal shift doesn't change, but the apparent distance would vary. So in that case, it will be this apparent depth plus this distance also. So that will be the total distance between the observer and the object. We'll take second case where, case 2, where the object is in rarer medium and observer is in denser medium. For example, you can think of the bird as seen by a fish. So in that case, the bird is the object which is in air and the fish is the observer. So imagine that a bird is trying to attack a fish. In that case, fish could use this concept to escape, but then fishes or birds know these things by evolution. Let's draw this. We have boundary and let the upper medium be the rarer medium and this the denser medium. So its refractive index we'll call as NR, and for this we'll call it as ND. Now suppose somewhere here an object is present. Same as in the previous observation, we'll take one light ray which falls normally on the surface, and this light ray moves undeviated, moves as it is. We will take one more light ray which falls at an angle to the surface like this. Now since the light ray is moving from rarer to denser medium, this light ray would bend towards the normal. It will bend and go something like this. It is bending towards the normal. If we draw this light ray backwards, it appears as though it is coming from some point here. So this point would be the image of the object, we call it as I. So distance between the boundary and this O is called as X real. Distance between the boundary and the image is called as X apparent. Now even here also observe carefully that it doesn't matter where the observer is, whether the observer is somewhere here or somewhere here or somewhere here, doesn't matter at all. But what would matter is the effective distance between the image or the object and the observer would matter. So in this case, x apparent, we need to find x apparent here. We'll first find x real. In this case, x real is less than x apparent. So therefore, x real is equal to x apparent into x real is less than x apparent. So it becomes nd by nr. No, I'm sorry. It becomes nr by nd, because in this case x real is less. So from here x apparent is equal to x real into nd by nr. The same way you can find normal shift also. The normal shift in this case would be x apparent minus x real. Try and see it, you get the answer for here also. So this is a normal shift, and effective distance matters on the observer also. Do remember that normal shift doesn't matter while the effective distance, which means distance between the object and the observer, will change. For example, this is some distance and this is different distance and this is different distance. That matters. While this shift here doesn't matter at all. The observer is somewhere here or here, doesn't matter at all. The next topic is consequence of refraction. There are many consequences of refraction. An example we saw is bending of pencil or bending of say something put in water, like a stick put in water. There are many examples of refraction which is seen around us. One more example could be the twinkling of stars. But what is given in syllabus is about early sunrise and late sunset. To understand this, think of the sun as seen here. We'll think of the horizon. So horizon basically means, it is called as line of sight, which basically means the point where the sky and earth appear to meet. It's called a line of sight. In this case, if you look at this as the earth's surface, and suppose somewhere here there's observers say standing, this line of sight is called as horizon. If the sun is below this point, just put a red dot here. If sun is below this point, it means sun hasn't yet risen. If sun goes below the horizon, this side, it's already set. Now in this case, early sunrise means that even though the sun, will call this as S position, even though the sun is below the horizon, what happens is, because of refraction, even though the sun hasn't risen, but because of refraction, it appears as if the sun is somewhere here. So this is called as early sunrise, which means the sun hasn't risen but appears to be risen, as seen in this case. Even here also, suppose the sun is already set, but because of refraction, the sun appears to be still not yet set. This is called as late sunset. So early sunrise and late sunset is because of refraction only. To understand a better way, as seen here, this is the Earth's and something around it. This is called as atmosphere. Atmosphere is a thin blanket of air surrounding the Earth. It has a very small refractive index compared to other medium. We saw in classes that we took value of n for air as 1. But actually, the value of n for air is slightly more than 1. Not exactly 1. But that becomes important in this case. Otherwise, if we take the value of n is equal to 1 for air, then we can't understand refraction and this phenomenon. Now here, since the value of n is slightly more than 1, so what is present around the atmosphere is vacuum only. So for vacuum, the value of n is equal to 1. So for atmosphere, it's slightly more than 1. Now, if you look at the Earth's center, this is the Earth's center. At this point of contact, if we draw normal, at the first layer, the light ray is going from rarer to denser medium. In this case, the atmosphere, which is air, becomes the denser medium compared to vacuum. So, since light is moving from a rarer to denser medium, light would bend towards normal, but then the difference in refractive index between vacuum and atmosphere is very small. So there's a very small deviation as seen here. It's a very small deviation. So light would bend towards the observer. So if we draw it backwards, it appears as if light is coming from some point far away. This diagram is highly exaggerated because it is drawn to explain the phenomenon. Otherwise, the difference is very small. We can't even see it promptly. But then it is still early sunrise and late sunset only. So the diagram here is drawn just to explain the phenomenon. The difference is not so high. As given here, the corresponding difference in time is actually 2 minutes only. It's a very small time. That is, the difference between the actual setting and apparent setting is 2 minutes. That is what is called as early sunrise and late sunset. We will take some examples to understand the earlier concepts. Example 1 says, if a fish is 40 centimeter below the surface of a pond, how deep does the fish appear to be to an observer directly above? Directly above means it's a normal shift, given refractive index of water is 1.33, which is same as 4 by 3. So here the fish is in water, and question says, how deep does the fish appear to an observer directly above? So in this case, the fish, which is the object, is in denser medium and the observer is in rarer medium. The fish depth is given. So what is given here is the real depth. Question says how much it appears to be. It's apparent depth. We know that x apparent is equal to x real into nr by nd. In this case, x apparent is equal to x real, which is 40 centimeter, into nr would be 1, and nd, because nr is other medium is air, nd here is 4 by 3. So 4 by 3, and from here it is 4 ones are, it becomes 10 into 3. It goes on top. The x apparent becomes 10 into 3, which is 30. Since this was in centimeter, even this should be in centimeter only. So it is 30 centimeter. It is common sense that the fish appears to be closer towards the surface, as seen in the earlier diagrams. Example 2 says, a thin glass beaker is placed above a glass slab which is 9 centimeter thick. So we'll first try to draw this. We have a thin glass slab, something of this kind, and this glass slab is 9 centimeter thick. So a thin glass beaker is placed above the glass slab. So on top of the glass slab, a thin beaker is placed like this. This is a beaker. To what depth should water be poured into the beaker so that the object appears to be at the glass water interface? So this glass slab itself, the second statement says, the glass slab is placed over a small object. So if you imagine that there's a small object, for example like a coin is placed here, then since you have two different mediums, this appears to be shifted normally. So question says, to what depth should water be poured in the beaker? So we need to pour water into the beaker. Question says, to what depth or to what height should water be poured so that the object appears to be at the glass water interface. So here this is the glass and water interface. So it appears somewhere here. Assuming the glass is very thin, we can think that this is the point where image is seen. This is called as I. So let the height of this be h. So height of the water to be poured is called as h. Question says how much of water should be poured. In this case, we learned that the normal shift in this case would be this height, which is same as 9 centimeter. You also learned that for compound slab, that is if you have more than say one object, the normal shift is given as it will be T1 into 1 minus 1 by N1 plus T2 into 1 minus 1 by N2. In this case, the normal shift is 9 centimeter because the object appears at the interface. So it is equal to 9. So write 9 centimeter. Do remember that it's in centimeter only. And thickness of the first medium. If you call this as glass, if you write this as say 9, it will be 1 minus 1 by, this is glass, and for glass the refractive index is 3 by 2, so it becomes 3 by 2 plus, this is unknown, so we call the height as h, that is if you call this depth as h, it becomes 1 minus 1 by the medium here, the material here is water, whose refractive index is 4 by 3. So it becomes by 4 by 3. So we'll solve this further. So 9 is equal to 9 into, it becomes 1 minus 2 by 3, 2 goes on top. So it becomes 1 minus 2 by 3, which is 1 by 3, plus h into, this term here is 1 minus 3 by 4, that is it is 1 minus 3 by 4 as 1 by 4, so into 1 by 4. So from here it is 3 1s are 3 3s are, if you bring this side becomes 9 minus 3, which is 6. So 6 is equal to h by 4, therefore h is equal to 24 centimeter. So if water is poured to height of 24 centimeter, in that case this object would appear at this interface. Example 3 says, find the absolute refractive index of a glass given that velocity of light in glass is 2 into 10 power 8 meter per second. Recall that absolute refractive index, which is called as n, was defined as the ratio of speed of light in vacuum by speed of light in the medium. So here n is equal to, the speed of light is a constant, which is 3 into 10 power 8 meter per second, and in this case it says given that velocity of the light in the glass is given. So here it is 2 into 10 power 8. So it becomes 3 by 2, which is 1.5. Here n is equal to 1.5. A very very simple numerical. Do remember the value of n for glass, which is 3 by 2 or 1.5, and n for water is 4 by 3, which is 1.33. Remember these values because these are standard values, and lot of numericals would be based on these mediums only. Example 4 says the refractive index of diamond is 2.4. Calculate the velocity of light in diamond. It's the reverse of the previous question. Here the diamond's refractive index is given. Question says find its velocity. So n is equal to c by v, or from here v is equal to c by n. C is a constant whose value is 3 into 10 power 8, and n here is 2.4. So you can write this as, if you multiply and divide by 10, it becomes 30 by 24 into 10 power 8. It goes in 6 4s are 6 5s are, so it becomes 5 by 4, which is equal to 1.25. The velocity here of light in diamond would be 5 by 4 into 10 power 8, which is 1.25 into 10 power 8 meter per second. Again, remember the value of n for diamond, which is 2.4, because we will do some examples or some applications based on this. Thank you.